It's my great pleasure to introduce Vidya Muthukumar from Georgia Tech. Vidya is an assistant professor in the Electrical and Computer Engineering School and in the Industrial and System Engineering School at Georgia Tech. Vidya research spans over various aspects of machine learning, including a series of great works in the area of overparameterized machine learning. We have recently co-authored an overview paper on the recent progress in this area, and it was great working together on it. And I'm sure that this talk will be a great talk and a great contribution to the TOPML workshop. So Vidya, the stage is yours. Thank you very much.
Thank you very much for the kind introduction, Yehuda, and thank you for organizing this wonderful workshop. It's my great pleasure to be here. So before I get into it, let me know if you cannot hear me at the earliest. Great. Okay, I guess people can hear me, but let me know at any point if that's not the case. I usually have at least one technical glitch in all of my talks. Okay, so thanks again, Yehuda, for the very nice introduction. It's my great pleasure to be here. And today I'll be telling you a little bit about a line of work that we have conducted in comparing directly classification and regression tasks in overparameterized regimes. And there's going to be a lot of discussion of various types of training and testing loss functions in this talk. Okay, on cue, I have a glitch, but hopefully should be, I'd have to stop sharing and share again. Sorry about that. Great. Okay, so without further ado, I'd like to thank my many collaborators on this line of work. A lot of these discussions actually started about a couple of years ago at the Simons Institute, where we were starting, overparameterization was really a burgeoning area at the time. And we wanted to really investigate the ramifications of these overparameterized models, specifically on classification tasks. So just to start with a very little bit of motivation, I think given the audience of this workshop, I can safely assume that everybody is interested in various aspects of overparameterized models and that at least all of you have seen some version of the double descent curve. What I want to do is actually mention a couple of things about the original experiments conducted by Belkin et al. First of all, these phenomena have been observed for both regression and classification tasks. But also, interestingly, some of the original experiments were run with the squared loss. And since the advent of these experiments, we've seen a lot of wonderful mathematical work analyzing overparameterized linear models in the case of regression tasks, and comparatively less for the case of classification. And what I'm going to focus on today is basically, specifically the classification task. So in today's talk, we're going to be doing a lot of direct comparison between classification and regression. And really the whole story boils down to a tale of two loss functions. So starting with the case of regression, the picture is really kind of simple in the sense that what we really care about at test time is to predict as close as possible to the real valued outputs. And our error metric is typically the squared loss, or rather the mean squared error metric. And accordingly, this is a reasonably well-behaved loss. And so at the training time, we also minimize the squared loss. On the other hand, for classification, what we mostly care about is something like a 0-1 loss. For example, if we want to classify cats and dogs, we may not care so much that our real valued output actually looks different from a cat, as long as the ultimate prediction that we get is in fact that of a cat and not of a dog. So in the classification setting, we really care about a 0-1 loss. And since the 0-1 loss is discontinuous and not well behaved, typically at training time, what we need to do is train with a good convex surrogate to this. And in fact, in practice, the most popular such choice of training loss function turns out to be the cross entropy loss. In the case of binary classification, this is also called the logistic loss. So this is really the most popular choice in practice for classification problems. However, one could also use a squared loss to train on the labels directly. And this does have some historical precedent of being used in classification, although it is somewhat a less popular choice. And something somewhat surprising that we are going to see through the course of the talk today is that actually these choices of loss functions may not actually be all that different. So here's a rough outline of what I'm going to talk about today. Just to get everybody on the same page, I'll begin with a brief setup of the overparameterized linear model that we're going to consider. And I'll focus on the different types of solutions that we will study in both regression and classification. And after that, I will proceed to talk about the actual influence of different choices of loss functions, both at training and at test time. And through this talk, we're actually going to see that the loss functions play very different roles at these different phases of machine learning. And time permitting, I'll end with some discussion of consequences and potential kind of future directions of this whole line of work. So there are going to be some connections to the results I'll present today and the phenomenon of harmless interpolation and benign overfitting, some of them more direct than others. And I'm going to try and highlight these connections as we go through this talk. So if there are no questions about the basic setup, I think I'll go right ahead, but I'm going to pause for a moment to see if anybody has any questions. Okay, great. Let's get right to it. So we'll start with a basic description of our setup. And I'm going to start with a simpler case of regression, just a setup notation. So in regression, our output, which is denoted by y, is in fact real valued. And I'm going to assume a well-specified model in the sense that the output is a linear combination of d-dimensional features given by phi of x. So here x is the data and phi of x is the feature map induced by the data. And I'm going to consider additive noise of variance sigma squared. And typically the noise is going to have some well-behaved assumptions, such as being sub-Gaussian. I'm also going to, without loss of generality, assume that the features are centered. And a quantity that's going to pop up again and again through this talk is going to be the feature covariance matrix, which is just the second order information. So throughout this talk, all of the theoretical results that I'm going to present are going to make this blanket assumption that the features are sub-Gaussian and have independent components. And in fact, for some of the results presented later in the talk, we're actually going to assume Gaussianity on the feature maps. In some cases, some of these results can be extended to situations where we have more structured feature maps. A running example that I will use to illustrate some of our results will involve one-dimensional data, but the feature map corresponding to the first D Fourier frequencies. And this is actually a very useful feature model to get intuition for a lot of the phenomena that I will cover today. But all of the theory results that I will talk about will make this independent sub-Gaussian assumption. So since we're concerned with the overparameterized regime, throughout we're going to consider cases where the number of features greatly exceeds the number of samples. And what that means is that when we set up our training problem, where A here denotes the training data matrix and Y denotes the output, what it means is that we can in fact find an estimator beta hat that perfectly fits the training data. In other words, A multiplied by beta hat is exactly equal to Y. And in fact, there are infinitely many of these solutions. So for the purposes of today's talk, the solution that we will study and compare to will be the minimum L2 norm interpolator. And what this does is it simply takes the interpolating solution that minimizes the L2 norm of its weights. And note that this is equivalent to regression in the case where the amount of regularization goes all the way to 0. And you basically recover this type of interpolating solutions. Now, there are many other types of interpolators we could study. They're all quite interesting, but they're not going to be our focus today. Now, switching over to the setting of classification, we're still going to make the same types of assumptions on our features as well as the same type of well-specified assumption. But the main difference, like I alluded to early in the talk, is that the labels are now going to be binary valued. So in other words, the label Y that has been marked here is going to take values is going to take a value either -1 or 1. And this is actually going to be useful at various points through our talk. And according to this kind of model where y is going to be 1 or minus 1, the way the signal is going to interact is, instead of having this type of additive noise, we will instead have that the label is equal to the sign of the linear combination of the features. And there's a kind of a probability of flipping that label, which is given by nu. And that's what I've essentially marked as a label noise. Now, a lot of our analysis is, in fact, extendable to broader noise models, including the logistic model for noise, and there are many types of noise models we can consider. But for simplicity, I'm going to stick with this constant label noise assumption. So in the classification setting, the real departure from regression comes in the type of solution that we end up studying most of the time. And explicitly, the solution is called the hard margin linear SVM. So we call that we're in the overparameterized regime where the number of features greatly exceeds the number of samples. And so we are, in fact, able to perfectly separate our data. And the main kind of difference here is that our estimator is still going to have this minimum L2 norm bias, but the constraint is going to be somewhat weaker. Like, all we want to do now is we want to separate the data. We do not necessarily need to exactly interpolate it. And just to highlight the difference, if you look at what the minimum L2 norm interpolator would do in this type of a classification problem, this would also have a minimum L2 norm bias, but it would be subject to this much stronger constraint of perfectly fitting the binary labels. And noting that the labels are binary, what we can do is multiply both sides of the interpolation equation by yi's and get these stronger equality constraints where yi multiplied by phi of xi transpose beta is exactly equal to 1. So what this little illustration actually does is it actually shows us that, in fact, the minimum norm interpolator, which I'm henceforth going to just refer to as MNI, is feasible for the SVM optimization problem. However, the SVM in general could be quite different. There's no guarantee that the solution on the left-hand side of the slide and of the right-hand side of the slide are the same. Just to mention a few other differences between these two types of solutions, notice that the MNI, in fact, has a closed form expression. And this is actually kind of a fact that is used in a lot of the overparameterized regression analyses. On the other hand, the SVM does not, in general, have a closed form expression. So with that basic setup, what we are going to do for in the first part of this talk is directly compare these two seemingly very different types of solutions. And we're going to see some consequences for the choice of loss functions that is used under training. So before really getting into those results, what I want to do is actually review the roles of these different training loss functions in realizing these different types of solutions. And you can think of what I'm going to present here as just a crash course in the results on implicit bias of gradient descent. So what we will look at here is basically just the outcome of different choices of training loss functions under the linear model, assuming that in fact our data is separable by the choice of features that we have used. So starting with the hard margin SVM, a by now well-known fact that goes back to Daniel Soudry et al. And Ziwei Ji and Matusz Telgarski, essentially that if we were to train minimizing the logistic loss or the cross entropy loss running the gradient descent algorithm, our normalized weights would in fact converge exactly to the hard margin SVM solution. So the high level picture here is that we can obtain an SVM solution as a consequence of training with logistic loss and using the gradient descent algorithm. On the other hand, the MNI is obtained as a consequence of training gradient descent on instead the squared loss. And this result actually relies on a certain type of initialization condition that is initializing at 0. Nonetheless, we do get this, the MNI solution straight away from this. So just again to summarize how different these pictures seem to look on the face of it. Let's note again that the SVM is not closed form, and this implicit bias result is really insensitive to the initialization conditions. On the other hand, the MNI is a closed form expression, and in a certain conventional sense, it's considered to be the worst of the two solutions for a classification task. And finally, just to reiterate, this kind of equivalence between training on the squared loss and getting to the MNI is quite sensitive to the initialization. So I believe there's been recent work as well showing that if you initialize somewhere different, you would get to a different type of solution. So looking at this picture, it may really seem like the cross entropy and the squared loss, in fact, appear very different in nature, and they don't seem to be very directly related. They're coming from very different loss functions, and they have these very different properties. However, the situation in reality, maybe they're not actually all that different. And in fact, there's been both classical and recent empirical evidence that maybe these loss functions actually lead to very similar performance in practice. For example, Ryan Rifkin, back in the 2000s, actually wrote a lot of his doctoral dissertation on directly comparing training procedures for kernel machines with the squared loss and the hinge loss, and observed very similar performance across the two cases. And more recently, Poggio and Liao and Hui and Belkin actually showed that the performance is actually not that different, even in neural networks. So just to give a few illustrations of these empirical results, these are figures taken from the paper by Hui and Belkin. And what they show is the plots of test accuracy as a function of the number of steps of training or the number of epochs of training. And in all of these, the blue curves represent the accuracy that is obtained from cross entropy loss, while the red curves represent the outcomes arising from squared loss. And the figures going from left to right represent a wide range of tasks from NLP to speech recognition to vision. And what you see across all of these is, especially as you train for a longer number of epochs, you see essentially identical performance when the two different loss functions are used. Digging a little bit deeper into the actual numbers, we can also look at the accuracy as a function of the loss function used specifically on vision tasks. And for example, if you look at the table, you see in many cases, including very, very large scale tasks like ImageNet. So this is not just a phenomenon that you can see for smaller data sets like MNIST. You actually see that the accuracy is very similar across both of these squared loss functions, and at most there's a 1 or 2% difference either way. So these experiments are really very comprehensive. They're done across a lot of architectures and a lot of different types of application domains. And what they're really telling us is that it seems that you don't lose much from training with the squared loss. It's almost as good, in a few cases, maybe even better. So what we actually do is we have a set of theoretical results that essentially complements this empirical line of work and lends very strong support to it. And in particular, what we are able to show is something that at least initially was very surprising to us, which is that not only do these loss functions lead to similar performance, they actually can lead to the exact same solution. In other words, what we were able to show is that in sufficiently high dimensional settings, the hard margin SVM and the interpolation, these were the two solutions I showed a few slides ago, actually can exactly coincide with high probability. So the figure here shows an illustration of this equivalence. And in this figure, I'm considering 32 one-dimensional data points, and I'm doing linear regression with D Fourier features. And the value of D here is on the order of 1,000. Note, you can actually verify that this will actually be an isotropic covariance matrix that will come out of all of this. And the figure here actually shows the function fit that arises as a result of least norm interpolation. So that's the function fit in green, and the SVM, which is the function fit that arises in red. And you can actually see the exact equivalence manifest over here. The functions literally are right on top of each other. And our theoretical results, which, as I mentioned, are derived for the cases of independent sub-Gaussian features and Gaussian features, show that, in fact, you can show theoretically that these solutions exactly coincide with high probability under a sufficient amount of effective overparameterization. So to really interpret these results, let's recall some notation. So the vector lambda here denotes the spectrum of the covariance matrix sigma of the feature vectors. So in this Fourier feature example, for example, the covariance matrix turns out to just be the identity as a consequence of orthonormality. And in this case, the lambda will just be the vector of all ones. And in this special case, these results actually show this exact equivalence, provided that D is much greater than n log n, just looking at the condition on the right. So in this special case, our result is very easy to interpret. We are simply saying that these two seemingly different solutions actually exactly coincide with high probability, provided that the problem is sufficiently high dimensional. More generally, you can ask for the interpretation of these sufficient conditions in case of anisotropic covariance. And something that may be potentially interesting to note is that if you look at the ratio of lambda 1 squared to lambda 2 squared, that is in itself a kind of effective dimension that actually heavily resembles, for example, the types of effective ranks that are often used in benign overfitting analyses. I'm happy to take questions if anybody has any. I'm not sure whether I should stop for questions, although I'm also happy to keep talking. Okay. Okay, I guess I will. I think I do see a few questions. Oh, cool. Okay, so yeah, so I'm going to answer the question at the bottom, which is whether the function pictured here is a sum of cosines. Yes, that is exactly right. The function is a sum of cosines. So this is what I mean by doing linear regression with Fourier features. The betas are going to denote the coefficients that I recover as a combination of each of those features. Great question. Is the factor log n necessary? I will come back to that question. We did not show this, but subsequent work did actually show that this is necessary. I'll come back to this in a few minutes. Perfect. Thank you for the nice questions. Okay. So what I want to do going from here is actually say a little bit about the proof technique, and at least the first kind of step of the proof technique and what we really leverage to show this. Oh, sorry about that. I think I may have to start again. Okay, great. Sorry about that. So we're going to go straight to the proof technique. And the starting observation is going to be something that I'm going to call back to something that I said maybe about 10 to 15 minutes ago, which is, although like we discussed, there are many differences between these two solutions on the face of it, a starting observation is in fact that the set of MNI constraints is strictly stronger than the set of SVM constraints. And what that means is that beta hat MNI is always a feasible solution to the SVM optimization problem. So in order to show further that the solution is optimal, what we essentially do is we go to the dual formulation of the SVM, and we show that this primal candidate solution, beta hat MNI, is also strictly dual feasible. So it satisfies the strict constraints in the dual. And what that means is we can use the relationship between primal optimality and strict dual feasibility to show that this suffices for beta hat MNI to in fact be coinciding with the SVM. That is, for beta hat MNI to minimize beta 2, subject to the broader set of hard margin constraints. So just to walk you a little bit through that main proof idea, I'm going to denote the dual variables and note that there are n of them simply because the SVM has n constraints. And there's this very kind of beautiful interpretation of the dual SVM that goes back many decades. But the idea is that the VIs simply represent the proportion of support of each data point. And what I mean by that is that there's this very nice primal dual relationship between the dual variables Vi and the primal solution beta. In particular, we have beta is equal to the sum of Vi times phi of Xi. And we note that and by the way, these are for this relationship is for the optimal solution, not for all of the things. And we note that Vi is non-zero when it is basically when Vi is non-zero, we say that data point I is in fact a support vector. So what we really want to check here is for the strict dual feasibility condition for the solution obtained by the MNI, which is simply that Yi multiplied by Vi is strictly greater than 0 for all values of I in the training data set. And what we do is we basically notice that the MNI candidate dual variables have a very nice closed form expression. And this actually arises from the fact that we also have a closed form expression for the MNI. And our condition of strict dual feasibility basically just becomes looking at Yi multiplied by Vi being greater than 0, basically becomes like Y had a matter product with the dual variables being greater than 0. And we get this kind of fairly interpretable condition. If you kind of stare at this for a moment, what you would notice is that what we really, really want from this is that the training data matrix, that is AA transpose, should be sufficiently close in a certain sense to being a diagonal matrix. And just to do a bit of a thought experiment for that, and I do have a more detailed slide on kind of walking you through some examples in this that we can get to at the end if anyone is curious. But just to do an immediate thought experiment, let's think about the case where AA transpose was maybe exactly the identity. And in that case, the kind of dual feasibility condition reduces to multiplying each label kind of by itself. So you get Y1 squared, Y2 squared, blah, 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 up to Yn squared. And then each of those is going to be equal to 1 simply by the property of the binary labels. And we, in fact, will satisfy this condition. So in a certain sense, what is really nice about a diagonal matrix in the sense is that the labels do not interact with each other and do not cancel each other out. And the sense in which this does have a kind of implicit connection with benign overfitting is that it turns out that to be able to fit noise in a relatively harmless way, we want sort of similar phenomena occur in the overparameterized setting. In particular, a lot of the technical tools that are used in benign overfitting actually end up showing, for example, that this precise matrix AA transpose kind of scales with the dimension and is also approximately diagonal in some sense. So there is a type of synergy, I think, between benign overfitting and these types of equivalences between SVM and MNI that I've sort of touched upon, but I do not think has been fully explored. So the overall implication of this type of result is that, in fact, the training loss function may not quite matter. And that's just a consequence of all of the equivalences that I have kind of mentioned through this talk. Logistic loss leads to SVM and squared loss leads to MNI. And we have shown that these are, in fact, equivalent with a sufficient amount of overparameterization. So just to kind of reiterate, these corroborate old and new empirical results. And in the next part of this talk, we're going to see some nice implications of this equivalence. In particular, the fact that what we have basically established is that in these very high dimensional regimes, the SVM in fact has a closed form expression and can be directly analyzed just as a result of its connection with the MNI. So this forms a very nice story actually for the binary case. And it's natural to really ask what happens in the case of multiclass. And maybe before that, I see that there's another question. Okay, yeah, good question. So the short summary in this is that the conditions on A result reduced to conditions on the effective ranks of the covariance matrix. And what we basically need is and sort of an effective rank to be sufficiently large. So effectively high dimensional enough, but we actually need this I may be getting into too much detail here, but I'm going to try and answer anyway. Basically, starting when you count the eigenvalues, starting from the very beginning. So you don't quite look at the tail of the covariance, you have to look right from the beginning. So there is a sense in which the condition is stronger than required for benign overfitting, but it does follow that if you have this condition, you're also likely to have benign overfitting of noise. So that was maybe a short answer to that question, but I'll come back to that if it was not fully clear. Great, thank you for the questions. Okay, so all of this forms a kind of nice story for the binary case. And it's, if you may have noticed that in many places, we were really using the fact that the labels were plus or minus one valued. And it's very natural to, and we also used this kind of primal dual relationship in the SVM, which is really really only kind of the case in the binary setting. So it's natural to ask how much of this generalizes to the multi-class case. So what I'm going to do next. Sorry, I think every time I answer a question, there's this issue. Okay, so I'm going to kind of go over to the multi-class case. And this is actually a setting where I'm not going to get into too many technical details about how we are able to show that things work, but I'm very happy to talk about it offline. I'm mainly going to present the main results here. So in the multi-class case, as before, we have these sets of features and labels. And now what we're doing with the labels is we're simply doing a one-hot encoding of K classes. So for example, if the true label was 1, then Y1 will be equal to 0, and all of the labels corresponding to the other K-1 classes will be equal to 0. So accordingly, our classifier will also be a tuple of K weights given by beta 1 to beta K. And I'm also going to denote the true label of the data point by mi. So this is going to take a value from 1 to K, and basically y of mi will be equal to 1, while everything else will be equal to 0. And there is a notion of decision rule that is used in multi-class, which is simply looking at an input x and the candidate classifier beta 1 up to beta K. We pick the index that maximizes the linear product of these. And this actually, it's not difficult to show that this generalizes the binary case in the case K is equal to 2 and beta 2 is equal to minus beta 1. So as in the binary case, the objectives that are relevant here will also have a min2 norm bias. The reason I have a Frobenius norm is because beta is actually a tuple of vectors, and it's actually going to essentially be a matrix. But the picture gets a little more nuanced in the multi-class case simply because there are many different SVM formulations that one could consider. So for starters, I'm very sorry about this. I don't know, I'm having many glitches. I will maybe try to make this a PDF and start again. Okay, I'm going to try that again. Does that work, Yehuda?
Yes, it seems like it's working.
Okay, great. So I'm going to stick to the PDF format until now to avoid further glitches. Okay, great. So just to refresh, we're in the multi-class setup and we are looking at classifiers with a min2 norm bias. And really the devil is in the details. There are many different possible formulations for an SVM. So the one that you see here on the left is what you might initially expect. It's essentially encoding K different binary SVMs corresponding to the different classes. So for example, if you fix a class M, you see that you want to select your classifier beta m such that you have the hard margin constraint greater than or equal to 1 on the data points labeled with m and less than or equal to -1 otherwise. However, it's worth noting that this is in fact not exactly the same as the multi-class SVM, which is in fact the one that arises from the implicit bias of cross-entropy loss. And in the multi-class SVM, in fact, the constraints are somewhat weaker. Here, what you do is you consider the true label mi and any alternative label m for any given data point. And you see that what you're going to actually get is that the difference of these inner producted with the feature vector needs to be greater than or equal to 1. And it's not a particularly interesting algebra exercise to go through this, but it is something that you can verify, which is that in general, a solution that satisfies the one versus all constraints will also satisfy the multi-class SVM constraints, but this is not necessarily true, vice versa. So in some sense, the one versus all constraints are a lot stronger than the multi-class SVM case. And also the multi-class SVM case does not have quite as neat a primal dual relationship as we saw for the binary case. And of course, finally, we can look at the MNI, which arises from the squared loss, and the MNI would do something like interpolating these one-hot encoding labels. So despite all of these intricacies and kind of subtle differences between the different types of SVMs, what we end up kind of showing is that all of these solutions coincide in a certain sense, just like in the binary case, and despite the differences between these different formulations. So just to refresh our notation, and in a certain sense, what's also nice is that our sufficient condition for the SVM being equivalent to interpolation actually really resembles the condition that we saw a few slides ago for the case of binary labels. And the way we see this is we actually construct a certain adjusted label vector where you basically look at a certain class M and you collect all of the one-hot labels corresponding to class M on the n data points. And you subtract off this factor that's -1 over k, where k is the number of classes. And just to refresh, we denote the training data matrix as A. So in this setting, what we were basically able to show is provided that these adjusted training label vectors kind of commute in this nice way. So here again, the dot is a amount product and AA transpose inverse CM is kind of just as defined as before. And provided this condition holds for all the different classes, we show, for example, that not only are all the constraints active for multi-class SVM, and this part actually follows from just an extension of everything we did for the binary case. We also showed that this equality is satisfied in a very specific way. So in particular, we show that the multi-class SVM is exactly equal to the MNI on these kind of adjusted labels. And something I again want to note here, and again, happy to chat offline or send me an email and we can definitely go through all the details together. But something I do want to kind of mention here is that condition 2 does not follow directly from 1. And we actually had to introduce some new ideas and a new dual formulation to actually get to condition 2. So once you actually write out what these interpolation looks like, with this adjusted label vector, what we end up getting is this kind of interesting simplex structure on the predictions on various classes. And in particular, if we consider data point I and the classifier beta hat m corresponding to class M, what we end up getting is that the prediction value on the training data points is going to be equal to k minus 1 over k if that was indeed the true class of the data, and a smaller negative value otherwise. So this is kind of asymmetry induced into the interpolation and this kind of simplex structure that we found pretty interesting. So just to illustrate that structure a little bit further, the figure here shows a sufficiently overparameterized Gaussian mixture model where the number of classes is equal to 4. And the figure here shows the values of these predictions for the various classes. So the x-axis denotes the different classes, and the y-axis represents the magnitude of the prediction. So for example, just looking at the first data point, what you see is that the true class label was 4, and accordingly, the magnitude of the prediction on 4 is going to be much larger than the others, but in this very specific way. The magnitude is equal to, in this case, 3/4. And the magnitude of the other points is simply minus 1/4. And you can actually see a very similar type of structure happening for the other data points that are labeled differently. Another thing that I actually, just want to mention and tease a little bit is that I've said a lot thus far about how overparameterization is helpful for satisfying these types of conditions. Not entirely clear that it is necessary. So if you kind of look at what we needed this type of gram matrix to be approximately diagonal in some certain sense. And what we were also able to kind of show, and this was actually a consequence of some properties established elsewhere, is that under the neural collapse conditions, the same types of structure actually manifest. So we showed an interesting connection between this type of structure and the property of neural collapse. And just to see the intuition of that, if you think about what neural collapse is doing, it's basically just saying for all data points of class 1, the features kind of collapse and become very similar to one another. And we would expect that in a certain sense to be in line with the predictions of all such data points being exactly the same. And a similar phenomena turns out to happen for all the other data points as well. So just before I move on to talking about the implications of all of this on test performance, I want to just situate everything I've said in the context of some related work. So I talked a bit about implicit bias at the beginning of this talk. And as I mentioned, that kind of story says a lot about how we have these different types of solutions coming from different losses. Something I did not talk about much was the case of polynomially tailored losses. I think there are many interesting questions there to see whether these equivalences carry over to that setting as well. I'll also mention that a lot of these results were kind of situated in the non-asymptotic setting where the dimension greatly exceeds the number of samples. It is also very interesting to do these comparisons in the proportional regime using asymptotic tools. And there's a lot of nice work looking at such comparisons. And finally, I want to say a little bit about some interesting follow-ups to this line of work. So for example, Naveed, Clayton, and Daniel actually showed that the n log n threshold that we had shown a few slides ago is in fact tight. And you actually need the dimension to greatly exceed the number of samples. So you may not see this phenomenon of support vector proliferation in a proportional regime. And finally, in a more technical level, it is possible to extend some of these results to a more general sub-Gaussian case where the features are not necessarily independent. So that concludes the first part of my talk. I see a question here that I'm going to try and answer. Does this asymmetry change? Well, I guess by definition, we show equivalence to this particular type of structure. So if we change the offset, we would not in fact be interpolating that particular set of labels anymore. So yeah, for example, we do not directly interpolate the one-hot labels. We interpolate this kind of offsetted version of one-hot labels. It turns out that this does not affect classification performance. And that's kind of another nice property of the 0-1 loss. So all of this actually would affect regression performance, these types of offsets and so on. But for classification, it does not in fact make any difference, as we'll actually see in a bit. Okay, great. Okay, perfect. So we've said a lot about the equivalence of these loss functions, and we said a lot about how we get the same solution in both cases, even though we train with very different, seemingly different objectives. Now we're going to switch gears a little bit and talk about what happens at the test phase of overparameterized learning. Oh gosh, Sorry, try that again. Okay, yeah, let's move on. Great. Okay, so here's the basic setup again of the overparameterized linear model. And just as a consequence of everything that I've been saying until now, it suffices to study this nice MNI solution in the overparameterized regime. And this is very nice in a number of ways that we're going to see. Starting off, because the MNI has a closed form expression. So that's the first nice property we're going to use. And what we will do for the rest of this talk is now switch over and compare the role of loss functions at test time. That is the role of loss functions that are used to evaluate various tasks. So as I mentioned at the beginning of the talk, regression is evaluated according to the test mean squared error. That is, phi of x beta hat should be sufficiently close to phi of x beta star in a real valued sense. On the other hand, what we see with classification is that we only care about getting the sign of classification right. That is, the sign of phi of x transpose beta hat should not be different from the sign of the true prediction value. And hopefully you can already kind of see that this is a somewhat more benign metric. And through the rest of this talk, we're going to see this in a fairly dramatic way. So throughout this talk, when I talk about good generalization, I'm going to mean this in the sense of statistical consistency. In other words, we want the error to go to 0 as n goes to infinity. And we're actually, in most of these cases, going to grow d and n together. And we're going to consider d to be much larger than n. And again, I'll make all of this precise in just a little bit. So again, just to do a very quick situation in a related work, there's been a lot of great work understanding the MNI in the case of linear regression. Again, the starting point in a lot of this is the closed form expression of MNI. Comparatively less work in classification, although we've seen a lot of nice work in this space as well in the last 2 years. And just to reiterate, our focus here is going to be on getting nice non-asymptotic bounds and doing this in these very high dimensional settings where we grow d to be much larger than n. So again, we cannot say much about the proportional regime, and I think there's a lot of interesting asymptotic analysis there. So what I want to do before getting to our results is very quickly set the stage for the kind of specific covariates that I'm going to consider to state our main results. And in particular, I'm going to move away from considering isotopic covariance. And the reminder for why we do that actually comes from the observation that if we use isotopic covariance, we will not be able to preserve signal very well. So this is a very simple toy example that really demonstrates this. So just as before, I will consider these Fourier coefficients and an overparameterized regime. But just to make the illustration very simple, I'll assume that the data points are uniformly spaced. So note, for example, that the 0 line is given as reference, and this is, of course, not what we want. So note here that this is the true signal. This is ideally what we'd want to get to. And the problem with the MNI together with isotropy is that in addition to these types of function fits, it's also going to equally weight higher frequency fits that also turn out to perfectly interpolate the training data. And it's actually a very elementary signal processing calculation, but what you can ultimately show is that there are d over n such orthogonal perfect function fits or aliases of this data. And as a result of that, when you combine this together with the property of trying to minimize the weights, you end up getting a function fit like this, which is really bad from the point of view of signal recovery and results in a function fit that's very, very close to 0. And actually, if you look at a lot of the benign overfitting literature, what you'll see is that in the special case of isotropy, if you grow n and d together in this way, your error will tend towards the error that would be incurred by the 0 fit or the null risk. So keeping this kind of adverse picture in mind, we're instead going to consider an anisotropic model and one where effectively a small set of features is implicitly prioritized by the weights on the covariance matrix. So this is a model that is in fact inspired by many other contexts in high dimensional literature. For example, the study of spiked covariance ensembles. And philosophically, this is also what happens in function spaces with a bounded Hilbert norm and a sufficiently fast decaying set of eigenvalues. So the formal model that we're going to consider to state our results will be a high dimensional setting with a bilevel covariance. And what I mean by that is I'll have n training examples, d features, and b will grow, in fact, much faster than n. Remember, we want to be in an overparameterized setting to allow for benign overfitting in the first place. And the real kind of key to this bilevel model is that we're going to make two important assumptions on it. The first is that there's a small set of heavily upweighted features, and the number of such features is given by S, and this is going to be much smaller than both n and d. And finally, the ratio between these two levels of eigenvalues is going to also grow. And you can actually show in a certain sense that this is necessary for minimum for the MNI to generalize well, particularly for the case of regression. So what is the kind of consequence of studying this type of a model? Okay, sorry. So maybe before getting to all of that, just a couple of examples that kind of situate this. I'm not going to go into too much detail for these examples. And maybe before that, I'm going to try and answer a few questions.
Vidya,
yeah.
In like 7 minutes, we need to start according to the schedule, the next talk. So
okay.
We may allow, we can have a small drift of several minutes, but not too much. So
sounds good. Sounds good. Okay, I'll answer these two questions very quickly. Yeah, so you will not exactly get the red or the green fit if the points weren't sampled uniformly. That is true. But you will get some adjusted fits that are also orthogonal, and the same phenomenon as of kind of bleeding towards zero happens even if you had randomly sampled points. So the regularly spaced case is just is basically an exact illustration of what happens. Cool. So I'm actually going to move on with that and probably get to the main results. Sorry for all the technical glitches. Yeah. Okay, so the upshot of our main result is to simply show that in this bilevel model, classification is easier than regression in a very dramatic sense. And what it actually turns out is if you plug in the results of Bartlett et al., you would need the ratio between these two levels of eigenvalues to grow much faster than d over n for regression to generalize well in the sense that I described. That is, we need the error to go to zero in MSE as n goes to infinity. What we were able to show is that there's a much weaker condition on this ratio for which classification generalizes, but regression does not. And this is in a certain tight sense. So you actually have lower bounds for regression in this regime, showing that you would not preserve this property of good generalization. And finally, we got a completely tight characterization, which is on the figure on the left, you can see that neither of the two tasks would generalize well. And if you read the kind of diagrams here going from right to left, what you see is the figure on the right is a scenario that is good for both, while the figure in the left is a scenario that is bad for both. And the figure in the middle is one that is not good for regression, but still preserves the right 0-1 decisions and is actually good for classification. And I'll note here that there has been some historical evidence of classification being easier than regression, but this is typically in a more non-asymptotic sense in low-dimensional settings. So when we go to the overparameterized regime, what we were able to show is that this difference, in fact, becomes very dramatic. I think given the time, I probably cannot go into the main proof techniques, and I'm going to actually skip some of this. But what I will get to is mentioning the kind of implications of all of this at test time. So what we were basically able to show is that there is this kind of separation between classification and regression, and really the interesting part of this figure is right in the middle. On the other hand, then we want to kind of see how much of this carries over to the SVM. And for that, we really use the insights that we obtained in the first part of this talk, which were that the SVM turns out to be exactly equal to the MNI once we start moving towards the right in this figure. So we only need this ratio to be between the setting of square root of d over n and d over n, and then we actually get this equivalence. And the kind of ultimate payoff of our work is that we were able to find this setting in which the SVM generalizes well for classification, while the MNI does not generalize well for the case of regression. I'll also make a final comment about these results. If you look at the case where regression does generalize, which is the case where the ratio of the two levels grows much faster than d over n, one can get good generalization bounds for the SVM using bounds based on the training data margin, or alternatively sample compression bounds where the number of support vectors is relatively small. However, it turns out that these bounds actually do not give us or do not predict the good generalization for the situation in the middle. So they cannot explain this good performance that we actually get in the middle. And the kind of upshot is that the results that we get here were really, in a certain sense, derived through this explicit connection between SVM and interpolating solutions. And these are in particular not explained by the traditional margin-based bounds. So I also want to mention a couple of kind of follow-up and complementary results. So there was very recent, a couple of recent papers that I think in their own ways showed different types of separations between classification and regression tasks. For example, Don Harser et al. Showed this for under-general LP norms. And Shamir et al. Actually showed that they actually considered a misspecified setting, and they showed that classification can, in fact, be a lot more robust to misspecification than the case of regression loss. So I think these works are really nice in the sense that they kind of continue this theme that there's a very big difference between the choice of loss function that you're evaluating your problem on. So a couple of takeaways that I really want to mention here. So in the first part of the talk, we saw that the SVM and interpolation somewhat surprisingly exactly coincide. And the consequence of this is that very different choices of loss functions can yield very similar solutions. And later we took this insight to actually analyze the SVM, taking this route through interpolation. And ultimately we showed that classification is, in a very strong asymptotic sense, more benign. Like we can find high dimensional regimes where one of the tasks works and one of the other tasks doesn't. And this last point was one I did not have that much time to touch upon, but again, happy to chat about it offline, which is the point that classification can in fact work well, despite some of the adverse figures that I showed you a few slides ago, which is poor signal recovery. So maybe a kind of pitch I'll say about some of our results is that we actually showed that classification can generalize despite that property of poor signal recovery. Just a bit about current research directions. I'm thinking a lot nowadays about how to go from these independent feature models to structured feature maps. And I'm also thinking a lot about potential consequences of these separations between classification and regression for the case of adversarial error. And there are lots of very, very interesting open questions there. And finally, I already touched upon this a bit. Our results currently do not say anything for polynomially tiered losses, and I think it's an interesting mathematical question whether those in fact lead to different solutions. So that is it from me. Thank you very much. And I think, like Yehuda mentioned, we have a survey paper out where we made an attempt to summarize and explain recent research in this area. So very happy to get any feedback on that as well. Thank you again.
Thanks, Vidya. Great talk. Indeed, it's very interesting that different train loss achieve similar results. Great insights.
Thank you. Thank
we
you.
We have a bit time for an additional question from the audience. If someone wants to ask an additional question.
Oh, I think I answered the previous
there
question.
Is a new one, so
yeah,
so you
yeah. So okay,
and,
so is
and
it?
You can also ask by yourself from the audience. You're welcome to ask. So
yeah, I would love to take questions. I'm very happy to do that. Is it empirically observed in neural networks where classification is more robust than regression? That is a great question that I have been trying to figure the answer to out myself. I think the short answer would be that it really depends on the task at hand, and it depends on the type of architecture. So certainly there's been a lot of success of neural networks in regression in certain smaller scale settings. That is definitely the case. However, if you really look at the state-of-the-art neural networks, these are really applied to classification-oriented data sets. So if you look at MNIST, CFAR, and ImageNet, it's not entirely clear what the classification equivalent of those data sets actually is. Sorry, the regression equivalent of those data sets is. And it's not clear what a regression task actually looks like. Something else I will mention is that if you look at especially some of the earliest instances of adversarial examples, you would actually see that the initial so-called classification confidence was in fact pretty low in the first place. So if you look at the standard Panda-Gibbon figure, you might see that the initial confidence was something like kind of in the low 50s, and at least this is what I remember. So at least in some cases, this may not be all that good. And there are also other analyses showing actually that a kind of a more robust metric, such as classification calibration, may not be quite as good in the overparameterized setting. So yeah, I think there's a lot of interesting empirical questions as well in that setting that I'm trying to figure out the answer to. I'm happy to take any other questions, or yeah, I guess we have to go.
Yeah, I think we will proceed. Thank you very much. Great talk. Thank you very much.
Thank you. Thank you.
Let's all thank Vidya for a great talk. Thanks.